In the world of automation and Internet of Things, a navigational platform is required as a base functionality for public operation. The main functionalities of a navigational platform include lane following, obstacle avoidance, and obeying traffic laws. Under the guidance of Professor Amnitas, the results of this project is used to further his research on machine learning and robot navigation. The final product can be used as a platform for future researchers as well as robotics developers to build upon navigation and self-driving capabilities. The mission of the project is to develop a robot that can perform self-driving capabilities such as lane following, object detection, traffic signs detection, and obstacle avoidance. An additional goal of the project is to explore and improve robust functionality on a self-driving robot in an embedded system.
This project started with the Jetson TX1 development kit inherited from an earlier project on a similar topic. However, since the Jetson TX1 board has been removed from EOL by NVIDIA, making it difficult to implement NVIDIA's SDK manager to flash the OS, the hardware was changed to NVIDIA's Jetson Nano platform. The Jetson Nano is capable of producing 472 G-flops for running AI algorithms fast, running multiple neural networks in parallel, and processing several high-resolution sensors simultaneously. While the Jetson Nano is a high-performance computing module, it only requires 5 to 10 watts to operate, making it ideal for this project. In the slide, you can see the 3 hardware iterations this project went through.
Lane detection is one of the major problems that we're trying to solve. Researching papers suggest that there are 2 popular approaches to solve this problem. The first approach is using traditional image processing techniques. That's finding patterns from pixel values. Some of the notable methods are half transform based, inverse perspective mapping, threshold based, and edge based method. Recently, another approach that also brings a lot of promising results is deep learning, or using convolution neural network. The neural network can be used to either segment the drivable lane or detect the center of lane from a 2D image. Compared to the traditional method, deep learning is a more robust solution which can identify the lane under various lightings and road conditions. However, it is also require a large amount of training data and quite dependent on tuning the network hyperparameter. Therefore, our team decided to go with the traditional method.
In order to classify objects, our approach is to use deep learning. While traditional image processing struggles to detect complex objects like humans, cars, or signs, deep learning using convolutional neural networks excels at image processing, and many object detection systems exist that are open source, effective, and simple to use. For our project, we opted to use the neural network framework DarkNet, which is written in C, mainly for its compatibility with the object detection system You Only Look Once, or YOLO. We chose YOLO because compared to other popular object detection systems, YOLO is exceptionally faster, and the accuracy trade-off is very low in relation.
ROS, which stands for Robot Operating System, is the operating system used for this project. It is a standard in robot industry. It contains messages in ROS by using master and slave API with multi-thread synchronization. It is useful for integrating multiple programs that being developed at the same time. They already contain major API and library in the development of robot.
This slide represents our proposed solution and methods. As you can see from the diagram, this is the exact same one that we presented in the fall term at our proposal. If you could recall, the diagram is split into 3 parts, each corresponding to a term for what we hope to accomplish each term. Just to reiterate, the first term we hope to define the problem and project scope and then go into lane detection research and robot control implementation. The team itself divided into 2 separate teams to work on these issues, and along the line we would do material acquisition to suit our needs and to buy whatever we needed to continue our work. We also began creating our test environment as well. In term 2, we hope to go into deep learning research, which involves us figuring out what machine learning algorithm or deep learning methodology we wanted to use to best suit our needs. And the robot control team would begin development to develop the controls that we need to control the physical robot itself. At term 3, we want to achieve autonomous vehicle integration, which involves integrating both everything that we worked on onto the robot to see if it will all work together in tandem, and eventually test the solution and refine the solution based on the results we get from testing the solution as well. The lane detection algorithm was one of the first things we hoped to accomplish with the project. Given a video input, as represented from the bottom left image, the first thing to do to that would be to apply edge detection. The steps of edge detection are grayscaling the image, applying Gaussian blur, and performing the canny edge detection function, which is in the OpenCV library. This would produce the image on the second to left, the black and white image that's showing all the edges in the picture. After that, we would then perform lane detection itself. First, we would need to apply a region of interest function to isolate what we want to apply lane detection to. Of course, this will apply to the bottom half of the image because we only care about the lanes on the road and we do not care about the other edges in the frame. After that, the Huffline's transform function is performed to create line segments to show where the lanes would be. After that, taking all those line segments, we go into average slope intercept, which will group all the line segments together to perform the lanes that we see on the third image there. After lane detection, we would give all the information into a display lines function to display the lanes that we want to see. Granted, on that last image there's a lot more lines besides the lanes that we actually take note of. One of the big things is the blue line, or that distance line. That distance line represents the midpoint of the end of the lanes and a line in the center of the frame. Now, what this line does is that it helps us guide the robot, because if the lanes were in front of the robot, the midpoint will be right in the center, and it will line up with the center frame line. Distance will ideally be 0 or a negligible number to show that the robot is going straight in the direction and in the middle of the lane.
As stated previously, our solution to object detection involves training a YOLO network using darknet. We trained our network using the COCO dataset, which comprises of 80 classes and over 82,000 images. However, we found that running YOLO on a robot's live feed was still not performing fast enough to allow for an acceptable response time. Our solution was Tiny YOLO. On the left, you can see the architecture of the YOLO network, called DarkNet 53 for its 53 convolutional layers. Luckily, the creators of YOLO had a more compact version of the YOLO network called Tiny YOLO, which uses about half the filters at certain layers and is advertised to perform at least 11 times faster than YOLO. In our results, processing time went from 18 seconds to less than a second using Tiny YOLO, about 26 times faster. As shown in the processed images on the right, Tiny YOLO did lose accuracy, but is still able to detect and classify objects in the foreground while running fast enough to keep up with the live feed.
This should be our finalized software structure. It has RS core with control all of the node and 4 node image converter, object detection, lane detection, and PID with its control. Image converter going to convert image from the camera sensor to messages, and it will go into the object detection and lane detection to detect whether there are objects ahead or where the lane is, and those will come into the control to decide where the robot is heading, whether it have to steer left, steer right, or it have to stop before the obstacle ahead. The control will directly control the motor itself.
Because our project's goal is to create a platform for development, our end product would allow developers to save time while building autonomous systems. These systems could have a variety of helpful applications. For example, autonomous vehicles could help the elderly or disabled and reduce travel time. Or you could create a robot that is able to operate in environments hazardous to humans. Ethically speaking, self-driving vehicles bring up some complex ethical decisions. For example, in object avoidance, a situation may arise in which you must decide between saving the driver or the pedestrian. But how should a robot make such a decision? And this raises the question, how can you quantify morality, and who should be in charge of deciding such a thing? Another ethical issue involves the invasion of privacy that may occur when using cameras in public settings. Already, the use of traffic cams have been questioned by the American Civil Liberties Union, since they may be used to collect personal data outside of reckless driving. When using camera footage, the accessibility and usage of the footage must be monitored in order to prevent the violation of privacy.
Our original plan is to have a robot demo that can run both lane detections and object detection in parallel under the ROS framework. However, due to the COVID-19, we had to stop most of the development that we planned for Term 3, specifically the development of deep learning and ROS. The final scope is changed such that we want to make the robots that can detect and follow both straight and curved lane, and both the neural network and ROS framework is developed locally and not integrated to the final demo.
This is the final progress of the project. This diagram demonstrates what we were able to achieve in the past 2 terms. To compare this diagram to the one that was shown in the fall term, an obvious key difference would be the lack of Term 3. Unfortunately, we had to halt major development of the project for Term 3 due to the COVID-19 outbreak, therefore changing the scope of our project. In Term 1, we were able to define problem and project scope and begin splitting into 2 teams to work on lane detection development and robot control implementation. Fortunately, we were able to finish this by the end of Term 1 and therefore able to move up autonomous robot integration into Term 2. In Term 2, deep learning development and ROS development began, but unfortunately, due to the shift in scope, we were unable to integrate them onto the autonomous robot. The development of these 2 aspects of the project are on our local machines. We were able to get the lane detection algorithm onto the robot and it's able to move with the robot controls. We were able to test this solution and refine it as see fit. This is our current software architecture. Due to the change of scope, ROS could not be developed and completed, but we were able to get lane detection onto the robot and object detection on a separate system to operate as intended. On the robot, we have sensors taking in information and feeding that information to the lane detection algorithm. This, in turn, outputs the information we gathered from our lane detection algorithm and feed it into the controls. The controls will also feed information back into the system and give instructions to the motor to act accordingly. On a separate system, the object detection is able to accurately label the objects that the vehicle will have to avoid, such as cars and signs.
What we are presenting for our final progress is an algorithm that can successfully detect 2 lanes when presented to it. This works for both straight and curved lanes. In an instance that there is only one single lane presented, the algorithm will then use the opposite frame as a substitute until 2 lanes are detected. In addition, a proportional integral derivative controller, or PID, was developed to help smooth motion and navigation. Next, we have a neural network built with darknet anti-YOLO v3, which can track objects in real time, as well as recorded footage and images. The neural network was trained using the COCO database. We have set up the ROS workspace and laid the groundwork to build a functional framework. Initial implementation was started, however, due to the COVID-19 pandemic, the ROS could only be developed locally and not fully integrated with all functionalities. The current prototype can host the video in real time, showcasing what the robot sees and its lane object detection in real time. Multiple clients can access the live footage as long as they are on the same network. The Jetson Nano setup required installing NVIDIA SDK Manager with the latest OS image, installing developer tools for both host computer and developer kit, and installing the libraries, APIs, and documentation needed for this project. The Nano module has been assembled with Jetpack Kit to complete the hardware portion of this project.
For the next part, we will show the result footage that we collect throughout the process of working on this project. This footage demonstrates our robots running the lane detection algorithms and streaming the process image in real time. Users in the same network can view the footage using any browser and the robot's IP address. Due to the poor lighting condition of the room, the lane detection is sometimes unable to detect the lane, but this algorithm will run much more robust in a more open and brighter space. Next, this footage demonstrates our robots running both lane detections and motor control at the same time. The light conditions is very good in Basson Lab, therefore robots reliably detect both straight and curved lane. The motor control also worked well as the robot managed to stay inside the lane all the time. The next footage is a result of our object detection portion. We took a stock traffic mode footage and feed frame by frame to our trained neural network. As mentioned before, we used the tiny YOLO architecture to build and train our network. As a result, our network managed to detect vehicles and traffic lights in this video with a detection rate of 36 frames per second.
This is the responsibility of all team members. Yule, which is the project leader, in charge of the software of computer vision and deep learning, as well as oversee the whole project. Kurt Calvan, working on the RS, which is the integration of the whole project. Ethan, who is the leader in computer vision and lane detection. Gianna, working on the deep learning, the neural network for object detection. Hazem, we control the hardware of the robot and all the movement of the robot and integration of all physical parts together into the robot. This is the budget that we spent on the whole project. The power supply, battery, Jetson Nano development kit, the depth camera of Intel RealSense, the cardboard sheet and the painter tape which made the physical lane for our demo. The total of the equipment is $755.16.
Overall, even though we have to change our scope due to the pandemic, we managed to create a prototype with self-driving capabilities. We also provide documentations and code base for this project so that other teams can continue this work in the future. Thank you so much for listening. If you have any question, please contact us via our team members' email. Thank you so much.